oops, I don't know what just happened, is to take the derivative and see if it's positive or negative. But keep in mind the other thing we have to do is show that the limit as k approaches infinity of k squared over k cubed plus 1 is 0. And again, because the degree of the numerator is smaller than the degree of the denominator, I think it's a pretty safe bet that we all know that this is in fact 0. Decreasing might be a little harder. It will require that we take the derivative. So we're taking the derivative of the terms. It's another quotient rule. The bottom squared of the bottom times the derivative of the top minus the top times the derivative of the bottom. Oops. This is a little easier algebraically. The k cubed plus 1 stays on the bottom. That's again still very positive. In the numerator, we get 2k to the 4th plus 2k minus 3k to the 4th. So we end up with negative 3k to the 4th. No, negative k to the 4th which is not decreasing for all values of k, but it's decreasing for values of k that are larger than 2. I know that because if I factor out a k, I'm not even sure my algebra is correct. What I really mean to say is it's decreasing for values of k that are greater than the cube root of 2, which the cube root of 2 is going to be a little bit larger than 1, so this still holds true since k are integers, the k values are integers, so when k is greater than or equal to 2, this is decreasing. So again, most of the time, it doesn't have to be decreasing starting at k equal to 1, as long as it is eventually decreasing, all things will still hold true. So there's only one term from 1 to 2 it's increasing, and then it starts to decrease afterwards. So it's decreasing, and the limit is 0 as k approaches infinity, which implies that this alternating series converges. Now, if we consider the same series, but I take the absolute value of this, now what happens? So again, we have the same similar issue happening where the alternating part becomes obsolete. If you're taking the absolute value of a negative value, it's obliterated. So we're really looking at k squared over k cubed plus 1. So now this means we're really looking at the series, k squared over k cubed plus 1. There will be several ways to show it, but do you know if this series converges or diverges? Thinking back to all of your possible series tests, every single one of them that I can think of will cause this to show that it diverges. So let's think about, first and foremost, doing a comparison or a limit comparison test. We could alternatively just simply do the test for divergence. This limit is 1, and in order for a series to converge, for a series to diverge, the limit can't be 0. So maybe we'll do the limit comparison test. The integral test would also show this diverges, but the limit comparison test is going to be the most straightforward to show that this diverges. So again, if you ignore any of the noise here and you focus on the highest powers, in the numerator and the denominator, k squared over k cubed plus 1, that would imply that you should compare to 1 over k. If we then take the limit as k approaches infinity of 1 over k squared over k cubed plus 1, you end up with the limit as k approaches infinity of 1 over k times k cubed plus 1 over k squared, which gives you the limit as k approaches infinity of k cubed plus 1 over k cubed. And the limit again, because the degrees are the same, this limit would be the ratio of the coefficients, which is 1. If you recall, if you got a value that was greater than 0, this means that either both series converge or both series diverge. So the comparison we used was 1 over k. What do you know about 1 over k? You should be saying it diverges, which implies both series diverge. That leads us to the ratio test for absolute convergence. This is useful for determining absolute convergence, which also implies convergence. If you remember a few theorems ago, if a series converges absolutely, it converges. So suppose the sum of some terms, u sub k, is a series of non-zero terms. We will let rho equal the limit as k approaches infinity of u sub k plus 1, the absolute value of u sub k plus 1, over the absolute value of u sub k. And it's really saying the same thing as the ratio test did for our previous ratio test. If rho is less than 1, that means the series converges absolutely, which means it converges, even without the absolute value bars. If rho is larger than 1 or is infinitely large, that implies the series the original series, that's what I'm really getting at here, without the absolute value bars. In this case, it diverges. If it's 1, there is no conclusion and the test fails. So using that here in example 1, we will take the limit as k approaches infinity of the absolute value of a sub k plus 1 over the absolute value of a sub k and see what happens. So that means we will be really just taking the limit of this without the negative 1. And that's really why the u is in here, so let me replace this a with a u, because that's really what they're trying to get at here. We're not, in this case, we are including the negative 1 as part of the, oh my gosh, I made a mess. We are including the negative 1 as part of the terms of this series, which is why we have to take the absolute value to exclude it. So this will be 2 to the k plus 1 over k plus 1 factorial. And for the sake of algebra, I'm going to flip the denominator. It will be k factorial over 2 to the k, because I'm really dividing by this, by the reciprocal of this. So rather than dividing it here, I'm multiplying by the reciprocal to save space. This will equal the limit as k approaches infinity of 2 to the k times 2 to the first over k plus 1 times k factorial times k factorial over 2 to the k. Stuff cancels, and we get the limit as k approaches infinity of 2 over k plus 1. What will happen to this as k approaches infinity? This will equal 0. What did the test say? The test said if that limit is larger than 1, it diverges, and if the limit is smaller than 1, which this is, it means it converges absolutely. Which implies our original series converges as well.